Welcome. Let's talk about primality and factorization. So these are key things as to how the RSA encryption is so actually secure, is because of these two problems. How do we determine if a number is prime and how do we factor a number? So let's talk about primality tests. Primality test is really asking how hard is it to know if a number is prime? If I give you a number, can you tell me if it's prime, yes or no? And think about what tests you have done. In your lifetime, if I gave you the wrote down number, just to do an example, let's do a small example. If I gave you the number, let's say uh, 47, and I'm asking, is this prime? You might be like, okay, let's test all the possible numbers that are smaller than it, all the prime numbers. So I test two. Nope. Let's test three. Nope. Let's test five. Nope. Let's test seven. Nope. Let's test 11. Nope. And you can keep going down this list: 13, 17, 19, 23, 29. The reality is a couple of things. All I had to do was actually check up to this point in time. Because anything that divides this, if this turns out to be two numbers, if this equals two numbers A and B, let's suppose that A is the smaller one, then we know that A is less than or equal to the square root of my original number. Because they can't both be bigger than the square root, at least one of the factors has to be smaller. So we always do is check up the primes. But the question is, how do I handle all these primes? Because that's a whole lot of primes. And I don't know, do you even have a list of all the primes? And the answer to that is actually we do have a list. It's just really, really hard to access, and that list is incomplete. So we might be able to find primes. In fact, that's the bigger example I have here is a ginormous, massive number. And these are actually the size of numbers we typically deal with in cryptography. In actual cryptographic encryption, we deal with numbers like this big. So if I have a number this big and I want to know if this is prime, Bob picks this number. His first thing might be to check all those prime numbers up to, let's say, 1,000,000. That's not even going to get up anywhere near the square root of this thing. This thing is huge. Not even touching it. That's nowhere near the square root. So he got up to the first primes all the way up to 1,000,000. That's a lot of primes. Now, Bob might be like, sweet, it looks like it might be prime. But then he tries 2 to the n minus 1 mod n and notices that that is going to give this huge, ginormous number. Now, the detail is not in the number. It's in the fact that that number is not 1. Because that number is not 1, it tells Bob that this is a composite number. It's not prime. How? I want you to pause the video and think about that just for half a second. All right, so I'm hoping you paused it and you think about. There's a theorem that we've been using this whole time, Fermat's little theorem. As a quick reminder, I'll just jot it up here at the top of the page. It says that for P is prime and P does not divide A, then A to the P minus 1 equals, or I should say congruent to 1, mod P. Let me rewrite that as an if then. If P is prime and P does not divide this number, then this is true. Now, if this portion over here is not true, then one of the first things must be wrong. Well, we know that 2, this massive number here does not divide 2 because it's smaller than it, which means the thing that fails has to be that P is not prime. So the Fermat's little theorem, it turns out, is actually a critical step in helping us identify that. And that actually is going to lead us to our very first primality test. It is related to someone known as the Miller-Rabin test. So let me tell you the theorem that the Miller-Rabin test is based off of. It's this: let P be any odd prime. So we're going to start with any prime, obviously starting bigger than 2. Beyond 2, every prime number, if I take p minus 1, that is going to be an even number, and so it can be written as 2 to some power times q, which q being odd. So in other words, I factor out all the 2's I possibly can, and then whatever's left is going to be some odd number. Q could be prime, Q could be composite, it doesn't matter, but it's going to give you this way. Then for any number not divisible by p, that sounds familiar like from Maslow's theorem, a to the q power is congruent to 1 mod p, or one of these is congruent to -1. Possibly all of them. Well, no. Once you get -1, the next one's 1, and it's all 1 from there. So but I'm saying it's possible that you may not get there until you get here, this last term. Because remember, so there's a little theorem that we've not really done in this class. It's that if I do n squared is congruent to 1 mod p, well, that tells me that n is congruent to 1 or p minus 1. Those are actually the only 2 options there are. And because of that, it actually opens up a huge world for us. So when we're squaring things, we get here. Now, it doesn't mean that you couldn't multiply by 3 and 3 times 3 couldn't be congruent. I mean, 3 times 5 couldn't be congruent to 1. It's not saying that. It's saying any number squared, this has to be true for. All right, so this idea is going to be the basis of the Miller-Rabin test, which is namely, we're going to take any odd number n. So it has to be odd because, again, we're talking a large number. We want to know if it's prime. So we're going to take any odd number, and I'm going to look at n minus 1 equals 2 to the cube. This is really easy to find because, again, if you give me any odd number, I can subtract 1. Super easy operation. I can then repeatedly divide 2 until I get a number that is odd. That is congruent to 1 mod 2. Same definition as odd. That number is q. Now, then I pick any number that its greatest common divisor with n is 1. Again, we have Euclidean algorithm. We can check this. Then the number n is composite if both of these conditions are true. That either a to the q is congruent to 1 or a to the 2iq is congruent to -1. Now, here's a to the 2iq for all those i's. Now, here's the catch-22 with this that you have to understand. Just because it fails this test does not make a number prime. In fact, there's a whole class of numbers that satisfy this test. I should say they fail this test, so that they're not composite. That I can't say definitively that they're composite, but that doesn't mean definitively I can say they're prime. This test only tells me, are they composite? Yes or maybe. And the yes is really strong. So we like this test because it's super easy to run. In fact, it's probably the #1 primality test that's used out there. And while it does not give you perfect answers, it does actually work super well. All right, let's talk about some other different tests there are. So another classic test involves something called Mersenne numbers. Now, Mersenne numbers are very similar because we're going to talk about Mersenne primes. A Mersenne number is a number of the form 2 to the n minus 1. So just so you can kind of visualize this, let's start where n equals 2. Then m2 is 3. M3 is 7. M4 is 15. M5 equals 31. So just stopping here, you can already see that 3 of them are prime. And that is awesome. So Mersenne numbers give us a number of prime values. Great. But what can I do with that? Well, what we can do with that is what's called the Lucas-Lehmer true primality test for Mersenne numbers. So first off, I need a number that's already in the form 2 to the n minus 1. How do you know if a number is in that form? Quite honestly, uh, first off, to know if a number is in Mersenne, all I do is I add 1. So I take n plus 1 and I divide that repeatedly by 2. And if that eventually gets me to 1, then we have a Mersenne number. If it doesn't, then it gives me odd at any point in time, we stop. And because we're simply dividing by 2 repeatedly, it's an order of log n. So that's a beautiful, easy thing to test. We can run this test, which is actually kind of an interesting test. So what we do is we define S1 to be 4. And then we compute Sj mod n. So we always start with S1 is 4. It's always our first value we kind of take. And then we're going to take that number squared minus 2 to get the next term in the sequence. And until we get up to n minus 1. So I compute this, this is a recursive function. I'm going to repeat it n minus 1 times. And then I'm going to check that last one to see if it's n minus 2 times, but I'm going to see if that is congruent to 0. Then the Mersenne number is prime. Otherwise, it is composite. So this is a really beautiful part. This one, if it's a Mersenne number, we can definitively say it is prime or it's not prime. But it's only for Mersenne primes. So let me do a quick example, show you how this works. So let's take the Mersenne number 13. So that's 2 to the 13 minus 1. It's 8,129. So we're going to compute the least, I'm going to do S bar because I'm just taking these things. So you can kind of see. So remember, each one I'm going to take 4. I'm going to do 4 squared minus 2, which is 6, which is 14, mod this. And then I'm going to take 14 squared, which is 196 minus 2, 194, mod 13. And we keep repeating that process all the way down till we get to S12, which happens to equal 0. So because of that, again, going back up to the definition, if it's congruent to 0, mod n, then M13 is a prime number by the Lucas-Lehmer test. So this gives us all of our Mersenne primes. Even Mersenne primes, we've not found all of them. Like the largest one, I can't remember. It's huge because it's a wonderful test. But I have to find a Mersenne number, and then I have to, and that's that. Once it gets to a certain size, it becomes really, really complex. And n just really makes it hard. All right, so let's talk about in general, why is this whole thing so hard? It's actually what's known as the density of primes. That means how frequent do primes occur. So if I call phi of n is the positive number that denotes the number of primes not exceeding, I'm sorry, phi of x or phi of n, I've seen it both ways. So let me do a quick example of this for you. Phi of 2 is 1. Phi of 3 is 2. Phi of 10, and this is where it gets funky. Well, how many prime numbers are smaller than that? It's 4. And if I go if I go phi of 11, it is 5 because not exceeding means it includes, and since 11 is prime. But if I jumped up 1 less than it, phi of 9, that would have also been 4. So this is one of those things where it's kind of weird. It's in this case, it'd go 1, 2, 2, 3, 3, 4, 4, 4, 5, 5, 6, because at 13 it's going to go to 6. So it just has this pattern it's kind of inconsistent. There's not an equal spacing, and that's what makes these super hard. But what we do know is this. This is a really cool theorem that was proven a long time ago, and it involves limits. I know this looks horrible and ugly, but the ratio of the number of prime numbers to x divided by the natural log of x, that ratio goes to 1 as x goes to infinity. What does that mean? And by the way, the reason we do x is because technically we allow this to be any real number because that allows us to actually do more analysis than just integers. But that legitimately means that the number of prime numbers um, is if you take the any x numbers, phi of x divided by x is going to be approximately the natural log. So this thing right here is actually going to approximate I'm not even saying this right. So this statement right here. So if you write it at so I can write this way, phi of n over the natural log of n. Well, that's the same thing as phi of n over n times the natural log of n over 1. I'll put it over 1 because I can just take this and I can essentially flip it. But this thing equals 1, or it's approximately 1, as n is really, really big. If I divide both sides by n, that means that the number of prime numbers less than or equal to n divided by n is approximately 1 over the natural log of n. That is what this means. So if you choose any random n value, the probability of that number being prime is approximately 1 over the natural log of n, which I will tell you, as n gets really big, the natural log of n gets big, so the probability grows smaller. So that means it's really hard to find prime numbers. This is the classic problem. It's part of the reason that RSA is really secure, because remember, we wanted 2 large prime numbers. So you find the prime numbers and you keep them secret, and it's really hard for everyone else to find them and know which ones they are. All right, so that's prime numbers. I'm going to stop here. I'm going to come back and make the second part of this video to talk about factorization.